Good afternoon to Dr. Jayanti and my friends. I am Siti Sarah. My metric number is 194324.
I'm Tiong Xiaohui. My matrix number is 192640.
And today we are presenting a research paper with title Using Time Series Analysis to Predict Disease Count with Structural Changes. So, hello everyone. I will start with the introduction first. So, in this study, we are using the time series analysis to predict disease count with structural changes. And as we all know, the time series is used to build model of trends, predict disease count, and also utilizing historical data. And the problem is this time series may experience changes which are divided into two. Outbreaks and also structural changes. And in this research, we are focusing more on structural changes. And to overcome these changes, Zhu and Xiao has proposed a method called non-parametric U-statistic. This method is proposed to detect changes in the time series analysis. But the problem with this method is that it is only capable of targeting smooth changes, while time series of disease count in public health surveillance may experience abrupt changes. And in addition, it assumes the stochastic component complies with autoregression and finite and non-lag order. And this will result in the limitation in the analysis in the presence of parameter uncertainty, which is a vital component in predicting disease count. So the next one, what they do to overcome this problem with the method proposed by Zhu and Xiao, they are utilizing chance method, which is local estimators for estimation near boundaries. For this method, we are unable to predict disease count accurately because it can detect abrupt changes that happens in time series of disease count in public health surveillance. And in addition, it can also model parameter uncertainty. So as we have talked about earlier, there are two limitations of Zhu and Xiao method which lead to the utilization of chance method. The first one is this method only focuses on smooth structural change, whereas the time series of disease count in public health surveillance may experience abrupt changes. And it assumes stochastic component of the time series complies with auto-regression and known and finite lag order. So this will lead to an inaccurate prediction of the disease count. So the objective of this study is to propose a new method to reduce the limitation of Zhu and Xiao methods, which is the new method is chance local estimator for estimation near boundaries.
Okay, so now I will move on to the methodology part. As you can see, actually we apply 5 different approaches to finally get this new proposed model. First of all, in order to derive the new proposed model, we use Anderson's definition of time series. This series have this formula. First of all, the observed series equals to sum of trend t plus irregular t. Trend is actually a deterministic function, which is if you give the same input, you will get the same output. But for irregular t, it's actually a random function, so it will get a different output every time. For irregular t, the formula we use in here, we use lag. R lag equals to 1 minus summation pi lag. This formula actually is used to count the unconditional volatility. So now next we move on to this. We use U-statistic, the existing proposed model, plus chance local estimator to create the new proposed model. In Chance Local Estimator, we actually select the linear regression model and we use least square method to count for the abrupt change. So actually this is for the abrupt change, while this is for the structural change. Structural change means that it's like stable change, but abrupt change is for like the random changes. Okay. So this new proposed model is actually used for the disease count later. Besides that, we also use the prediction process. This is to reduce the bias in the data. We actually use 3 prediction process in this study. First of all is 1-year prediction process, 2-year prediction process, and 3-year prediction process. Since the data we collected was from 2007 to 2017, for 1-year prediction process, we use 2007 to 2016 as the data collection, then we test on 2017 data. For 2 years, we use the data from 2007 to 2015, and 2016 and 2017 data will be used for prediction process. For 3 years prediction process, we will collect data from 2007 to 2014. Then the year 2015, 16, and 17 we use as the prediction process to see actually the data collected was correct or not using this new proposed model. So next, finally, it will be the Q-score. The Q-score is actually to see the competency of the new proposed model. And actually it's used to see how much a method improve the unskilled random prediction. So the lower the Q-score, the better the performance of the model. Next. So now let's move to the result part. In the result, we get proposed method versus existing model without configuration or upgrade method. This one is actually the model which we use statistic without the Chinese local estimator. Yeah, so in this comparison, we found that proposed model is far better than the existing method by comparing the Q-score. The Q-score actually shows that the proposed model has the worst Q-score, which is actually outperform all the existing model. So next is the comparison between proposed model versus alternative method of structural change. Basically, every comparison of the Q-score shows that the proposed model has lower Q-score. But for one result, 1-year prediction of syphilis, which is a disease, which shows that proposed model is not as good as alternative method of structural change. But it's okay because out of that much of data, it's only one data is not fulfilling. Yeah, and I think it might be because of the 1-year prediction. Okay, so now we also found that the proposed model in predicting disease count using 1 year, 2 year, 3 year prediction process is actually the same. That means the data we collected from 2007 to 2017 is kind of accurate except this 1-year prediction of syphilis. Okay, now next. So in conclusion, the existing method we use is not enough and is only accountable for small structural change. However, the new proposed model with local estimator, Chinese local estimator, can detect abrupt change, which is a combination of trend T and irregularity. So why we are using new proposed model is because there's another element such as vaccination, which will affect the result of the method used to predict disease count. This is actually seen with the time series literature, which state that parameter in deterministic function, which only apply trend T, that not vary over time because it was the same input and same output. That's why it's actually incapable to predict uncertainty. However, our new proposed model, we have structural change and temporal change together, so it's much more capable in address change in trend.
Okay, now I will explain to you about future work. As we all know, this research has some limitation, and future work needs to be done to improve the research. And the first limitation is that we found out that contribution of this proposed method in some disease is more effective than the others. So what we can do for improvement is that researchers in this area is encouraged to design and implement studies to see if the contribution of this proposed method relates to the nature of the disease. And the second limitation is that the data in this paper is limited only to Northern Nevada. So to provide better understanding of this proposed method, we are encouraged to expand the data sets on a wider range of disease from different geographical location and also with higher sample size. And the last one is different set of disease will lead to different results. So the researchers are encouraged to do future studies evaluating the method with different set of disease. That's all.